I would like to thank Dr. Edwards for the invitation, and actually my first time to be in this center. And also, I think it's the first time I present this topic to this community. And it's about quantum computing. Quantum computing. And essentially, when we hear about quantum computer, we always ask the question whether this is really better than classical computer. And now people are trying very hard, both theoretically and experimentally, to show this is really better than classical computer. But still, we are not there yet. Somehow, there are two groups. One group is for quantum computing, and they try to run quantum algorithms experimentally, and showing this is better, and we can solve some problems. And then the other group is from classical computer side. They say, okay, we can find better classical algorithms, and okay, so far we can beat quantum computer for this small size quantum system. So it's not yet clear when we will reach this critical point. And but recently we have some better understanding where is quantum advantage, and I think we'll reach to that point very soon. And certainly, when I learned this stuff, and first time I realized, okay, this is more or less just linear algebra plus tensors. Why it's so fascinating and why it's so powerful. And actually, when I look at those classical computation algorithms, they don't really use that much beyond linear algebra, tensor statistics. And, but at that point, 10 years ago, when I worked at Harvard with Arthur, we try to bring ideas in subject theory and topological quantum field theory to build a better language compared to tensor network and more efficient computational rules so we can understand the structure better. But somehow it's very hard to convince quantum computing people mathematics is better. They don't trust the theory. They just trust the numerical simulations. That's really painful for me at the time because we have those kind of three-dimensional structure like 2 + 1 TQFT and a lot of more or less picture language and scale relations. Theoretically it's good, but what they want to see is numbers. They want to see, okay, we can compute this number faster. And then we have to use classical computer and run some programmings, use some code. I'm not good at that at all. Until when I get back to China and I talk with many of my students, and they are good at that. So now we can implement that in a better way, and we have several good programs to show the idea, the most mathematical idea, really can improve our understanding of quantum advantage. And today I will present several examples and our recent work. The first quantum computer is interdisciplinary topic. Even on the theoretical side, it's has this big overlap between mathematics, physics. Somehow we should understand all three parts. To understand the different favor, the different groups. And on the other hand, if you really want to implement this experimentally, there are a lot of engineering problems. It's more technical. Yeah, but today we will mainly focus on the theoretical part. And well, why we are so interested in quantum computing, in particular in recent years, because classical computer is really reaching the limit caused by Moore's law. Previously, the computational power by classical computer is doubled every year. But now we are reaching this minimal size, and we really need quantum physics there. And somehow we don't want to build a classic computer using quantum physics. We really want to use quantum physics to build a quantum computer, and that could be much, much better. And this quantum computer idea has been proposed by Manin and Feynman in 1980s. Somehow they saw, okay, physics system is very complicated. Like many people talk about quantum field theory, and we all believe most of them cannot be computed classically. And then since they are quantum, we should expect to find a real quantum machine to simulate quantum system and have a better computation. And this has been very successful for small models. And here are some basic ideas we will bring from the quantum physics. Even much easier compared to operator algebra, since in operator algebra we need a big Hilbert space and the different states or the states of the Hamiltonian. But for quantum computer, for a single qubit, we only need the ground states and the first excitation to represent 0 and 1. And also in quantum physics, we can have their superposition so that this quantum memory could be bigger than classical memory, which is just 0 and 1. This is superposition. And for the measurement, it becomes very interesting when we measure. Somehow we cannot get the information, fully get the information, but we can measure that, and then we will get the 0 and 1 improbability. So if you want to read the full information of the state, essentially you need to measure this frequently, and also measure that not just in one basis, but in different bases. Otherwise, you only see the diagonal information. But this involves the exponential cost. So if you have an n-qubit state, that's in c to the 2 to the nth tensor power, if you want to know the density matrix in full, essentially you need exponentially many sampling or measurements to take this information. That's kind of the major difficulty, one of the major difficulty. If we want an exponential speed up, then we have to overcome this. We don't want to take exponentially many sampling. That's just not better than classical computer. And another thing that really gave us a good speed up for quantum computing is the transformations. We can implement a unitary gate. And this can implement somehow the parallel computations on the superposition of the states. And this gives us more computational powers. And most of the quantum algorithms actually focus on elegant implementation of such unitary gate for some quantum circuits. Here are some useful gates. So at the beginning, people want to say, okay, we don't know how to implement all those unitary gates, but we want a good generating set, and then approximate that. And first people thought, okay, maybe we have all the single qubit gates, and actually now the single qubit gates can be implemented experimentally with very high fidelity, like 99.99% for most quantum systems. And then for the 2 qubit gates, essentially you only need a CNOT gate or control Z gate, and that's enough. Kitaev showed that any 2 qubit gate is approximately a composition of such generating gates. And if we don't have all the single qubit gates, but just the so-called Clifford gates, they are stabilizers of the poly XYZ, then up to an error epsilon, you can still approximate the gate into the O epsilon to the -3 polynomial. That's good enough. And if you have all the angles, then you can implement the gate easily, like the Euler formula. The 3 rotations give you Upshur SU2. So those are the usual generating gates people try to involve and try to implement experimentally. And a landmark breakthrough was given by Peter Shaw's quantum algorithm for factoring large numbers. And this is very famous. And because this first, we all know what's this problem. And this is very difficult by classical algorithm, even though we don't really know whether there is a classical polynomial type algorithm, but so far not there. And Peter Shaw gave a polynomial quantum algorithm, so we can really factorize that efficiently. And this factorizing problem can be used to beat the RSA cryptography. Since that one used this factorizing problem, use the asymmetry to encode some public key and private key. And somehow, if you have a quantum computer, and then you can do it. So at that point, people get very excited, and in particular, people invest a lot in the subject, try to build a quantum computer. But now, by a rough estimate, even involving quantum error corrections, it will take somehow 1 million qubits to implement Shaw's algorithm to beat RSA 2048. And that may take 20 years. And there is a recent paper published at Nature from my colleagues at Tsinghua, Donglin Deng and his group. And they have a better quantum error correction code, so that can reduce that a little bit, but still it will take more than 10 years. So somehow we don't need to worry that much. And that also tells the difficulty to implement such quantum algorithm. And the major problem is our physical system is noisy. We don't have a perfect system. Otherwise, we can already do it now. But once we have noise, then it's not very clear. How can we handle such an algorithm? So in recent years, people are interested in the noise system. What do we really have in the lab? And we want to find some experimental demonstration that quantum computer can do something better than classical computer. And the first algorithm was given by Google, and that's called the quantum random circuit. Eventually, they have a 1+1 structure and taking some random weight. Theoretically, if there's no noise, they can show just the output, sampling of the output state. It's hard to be simulated by classical computer. But in the real system, since it's very noisy, so essentially they have a lot of techniques or very precise architectures to improve the result. And they try to argue they have quantum advantage, just this sampling process of the state. It's hard to be simulated classically. Well, there are two problems. One thing is, how do we know this is really hard to be simulated by a classical computer? It's hard to test. And actually, we don't really know what's the outcome of the quantum state. It's very hard to verify that. So they introduce something called cross entropy as a benchmark. And show you if something is above the benchmark, then it's hard to be simulated. And actually, there are some other circuits show you, okay, you can have similar benchmark, but it can be simulated by a classical computer. So it's not clear whether this is convincing. And another thing, more substantial, is given by a group from Chinese Academy of Science, a group from Pan Zhang. They really run this by classical computer, and they run something really technical. So that shows, okay, Google's 53 qubit random circuit doesn't have quantum advantage. But recently they improved that, to 32 qubit. And once you add a little qubit number, then the computational power of classical computer will increase exponentially. So it's still not clear whether we can do that by classical computer, but certainly it will cost much more. And another thing is given by USTC in China, that's in the boson sampling using linear photons. And that's another process to produce something that's hard to be simulated classically. For both circuits, there is a common problem. Even though we have those distributions, even though it's hard to be simulated by classical computer, but they are not useful. We cannot use them to solve some problem. So nowadays, the more important, maybe the most important problem in quantum computing is whether we can find a quantum algorithm to solve a meaningful problem. And that's hard by classical computer. So that's essentially the updates of this area. And there are many papers on the experimental implementation and many other papers on the classical simulation. Two groups are beating each other. Like for Google's paper, once it's posted, it's cited by, I think, more than 100 times just in 1 year. But most of them are saying, okay, we can simulate this by classical computer. So it's a very competitive subject at this point. So on the theoretical side, it's fundamental to understand the limitation of classical computing relative to the quantum computing. Like how far we can do classical computing. And actually, there are different methods. When they do classical simulation, they do use different methods. And somehow we want to see why those methods work and what are the mathematical structure behind that. And there are two well-known family of quantum circuits given by certain genetic sets. One is called Callifer circuit. Like those qubit gates, that's stabilizers of polywords. First slide. And those are known to be classically simulable by Gaussman in 1999. And those gates are very useful, even though they are simulable classically, but heavily used in the construction of quantum error correcting codes. And there are some reasons that they can be simulated classically. One thing is that the unitary group, the Callifer group, is isomorphic to a symplectic group over finite field. Actually, you can multiply this using some smaller matrices. But after you add the input and the measurement, then it's more subtle to say it's classically simulable, but that's done later. And another set of gates is called match gates. And it's more relevant to the Ising model. And it has continuous parameters and with genetic X and ZZ. And this can also be simulated classically. And this can be computed using so-called Pfaffin matrices, quite relevant to the partition function of the Ising model. And it's first given by Leslie Valiant in 2002. Somehow those are the two major families people study most that has classical simulations in polynomial time. And another approach is using the tensor network. Somehow we look at the generalization of linear algebras, but with more legs for multiple tensors. And then we can take tensor and contractions and compute that. And if the boundary of the tensor is not too big, say it's not no more than 30, then the vector space is below 2 to the 30. And that's doable by classical computer. And essentially, if you can cut a large tensor network into small pieces and compute every single piece by classical computer and do that in a good way, then you can compute the whole tensor network efficiently. And this is actually how they simulate Google's random circuit by classical computer. So this essentially rely on somehow the entanglement entropy between the local piece you have and the complement, somehow the number of boundary parts. And there are a lot of interesting development in this case. In particular, recently there are very less efficient evaluation of MPS, metric product state, using so-called DMRG. And just a lot of development in the tensor network. And also they have a lot of very nice code in GitHub so that people can use frequently. Now for us, we actually have this problem. We have better two-cavity language to do the computation, but we don't have those codes. And there's a very nice theoretical slide to help us understanding the essence of quantum advantage. Say you have the generating tensors, and then you just take all possible kind of planar tensor and contraction, and eventually you want to compute the value of the tensor network. And then for a fixed generating set, Jingyi Cai showed that this has the efficient or polynomial classical simulation if and only if the generating sets are the two families we mentioned. It's either Clifford or Matchgate. This gives a unique structure or behavior of these two families. And other than that, it's not just we cannot do that in polynomial time, and actually it's called the Sharpey-Hart problem. That means if you can another family in polynomial time, then you can solve all NP problems in polynomial time. So it's kind of either simple or hard enough, nothing between. This is something very interesting in computer science or complexity theory, and somehow in that sense we have a better understanding from the computational complexity of the two families. And what we know is that if we take the union of the two families, then we get everything. We get any quantum circuit from the union of the generating sets. Like the union involves all single qubit gates and the CNOT gates, as we mentioned at the beginning. And then we can write down all interesting algorithms efficiently, like Shor's algorithm. So people really want to understand how far we can simulate such kind of hybrid circuit or just a general circuit by classical computer. We know Clifford is fine, Matchgate is fine, but what happens if we combine them? That's universal. So we cannot expect a polynomial algorithm for all of them. Otherwise, we can solve all NP problems. But what's the limit? So people have tried a lot of effort in this direction. And somehow people take Clifford with some small numbers of match gates, like logarithm numbers, and then you can replace match gates as a linear sum of some Clifford gates. Total logarithm is still polynomial. And on the other hand, you can take something like match gates and plus a little Clifford, like two different approach. If you don't have much of the other kind, and then you can still do that efficiently. And also there are some mixing of the two structures, but with a very specific structure. That's somehow just something you can do classically, but nothing meaningful. It's just some kind of interesting mathematical problems, but no application in that favor. Just showing something can be simulated. But still, just even in recent 2 years, there are many papers talking about the mixing structure, how to simulate. And this is the long-standing open question after people see the classical simulation of Matchgate and Clifford. So whether there is a unified framework to classical simulate the hybrid circuit, which is efficient for both. If this is the case, then for this algorithm, what's the major difficulty? Essentially, we want to understand what is hard for classical computer. And that means this is something we will have quantum advantage. So we really want to understand that. And this is also the first open question I learned 10 years ago when I just get in touch with the subject. And for some reason, we will see, I believe we can solve this problem by the QAnon language. There are very nice mathematical structure behind that. But for some other reasons, we failed at the time. And until recently, we are able to give a very happy answer. Yes, now we have a unified structure. We can unify the classical algorithm for Clifford, for match-gate, for low-rank entanglement, and also not just the entanglement, but also topological entanglement, much stronger, and also some passive integral method, just all kinds of powerful methods. Now we have a unified framework. We can do all of them all together. We take all the advantage. So this really extends the limit of classical simulation quite a lot. So now for us, most quantum circuits have classical simulation. And in the first paper, this is based on a lot of work we have done 6 years ago. But because of this very sensitive conditions, we have difficulty to write this joint paper between China and the US. So somehow we solve another hard problem when we write this paper. In particular, the last author has to report a lot to the university to say why this is necessary to have such collaboration. And there is a more physics paper, and we try to explain the mathematical idea to the physics community, why this is so useful, in particular the TQFT and the QAnon language, why it's so useful. And in the second paper, we give this unified algorithm. We show how to unify those classical simulation methods altogether. So in second paper, we answer this long-standing open question. And this is based on the work joined with Jeffy and Alex Wozniakowski, where I was at Harvard. And that's called the QAnon 3D language for quantum information. And but at that point, we have better presentations of those gates, but not algorithms for gates. And until recently, this last 2 years, we have some other break in understanding of TQFT, 2+1 TQFT. And there we find much better understanding of the evaluation algorithms or the 3D scaling relations. And then we combine them. We say, okay, now we can solve the problem. But essentially, it's based on the two work. Now, and the summary of the main results, essentially, the Clifford circuits and match-gate circuits in our unified classical simulation are somehow the smallest set in the Venn diagram. We have a structure, mathematical structure, to characterize the quantum advantage. That's called the magic hole. It's a topological structure. And it captures the long-range phenomena, like topological entanglement, and that really gives quantum advantage. And somehow, if we want quantum advantage, we need some number of such magic holes beyond the logarithm. Otherwise, it's always simulable classically. And for both Clifford and match-gate, they have no magic holes. So very easy to do that classical simulation. And we also have some examples with a linear number of magic holes, but some specific examples. So far, this includes most interesting quantum circuits studied before. But still, we believe there are something that cannot be done by quantum computer efficiently. And essentially, this complexity is described by topological structure, rather than the usual thing that people studied in complex theory. That's very new stuff from mathematics. So what people used before is the tensor network approach, and that's like for a 3-qubit state or 3 tensors, we write it as a diagram with 3 legs. Here, I think for people studying tensor category planar algebras, this sounds very familiar. And actually, this is the most simple example because each space is just a 2-dimensional vector space, not that complicated. So how can we do better? We replace this by a diagram in TQFT with space-time boundary. It's just the fat graph of the original graph. So if you look at it far away, you get back to tensor network. But if you look at the macroscope structure, then on the space boundary, space-time boundary, you will see the additional decorations. Those are defects. And actually, this 2+1 TQFT, when we first proposed QAnon language, we don't really know what's the experimental meaning or physical meaning. Now we know that. That's another exciting part. Just we learned from some experimental group, they call something called space-time graph. That's exactly QAnon language. And we have much more mathematical structure. They take that as a diagrammatic notation, but we have computational tools. And somehow you can consider disk here, the disk as really a two-dimensional chip, a real physical chip. And this is the worksheet in the 2+3 dimension. And the line is just the defect point on the boundary. So all those manipulation will have some explicit physics meaning right now. We know how to do that. And in addition to that, we can have a lot of very useful rules. And somehow we are very familiar before. One thing is, when we have the lines, it's kind of the line for template by algebra, the simple object for SU2, two-dimensional representation. And then we can have the Brady, which gives the Jones polynomial. And then we can also have this Majorana fermions on the line. And we can also have this crossing with a parameter corresponding to the single qubit case. Now this is the dynamic Yang-Beckett equation that you can show just the breeding have all the things you want. So essentially, just you have the 3D structures, and you see something like the holes on the surface, and you will see those decorations or line decoration or crossing decorations on the surface. Those are the mathematical structure. And for classical simulation, we want to compute as a network. Now, on the other side, we want to compute the partition function of the TQFT using those diagrammatic relations, the diagrammatic decorations.
So when you say these are the ingredients of the tensor dynamic representation, are these like gates that you're using, or okay?
Yeah. Actually, those are the ingredients of gates.
Right.
You combine everything together, that becomes single qubit gate. So essentially, we open the black box in tensor network. Because previously, people considered this as a black box. It really looks black. But somehow we have some algebraic relations for tensor network. We don't know what's going on. But if we draw it in this way, then almost all algebraic relations here, they become topological isotopy, all Yang-Beckett equation on the other side. Something we understand much, much better. So essentially, you can think about that on the 2D boundary, you have the Ising model. And then in the bulk, you have the Chern-Simons theory, something like that. So this is really very meaningful thing to us. And that's something people trying to study in quantum computing. But just that the computer scientists are not familiar with those rules. So they are using something like that. And they found something parallel to TQFT, but parts of the computational rules, not the full picture. Now we found the complete list. So then with those structures, then what is Clifford? Clifford are given by just those surfaces with holes, and the crossing are just breedings. No dynamic parameters. And match gates has simpler bulk. That's a ball, 3D ball, with those crossings on the surface, on the sphere. So this is kind of the 3 ingredients and the 2 differences that this is just 2 of them. And this is observation we found when we first published this paper QAnon language in 2017. And in particular, if you look at Clifford, you will see those are data you have surfaces, you have those lines, and just braids. So essentially, you can write down all the information as bit rather than qubit. That's 0 and 1. And then it's very natural to ask whether we can find a classical algorithm using those topological data. It's a purely topological algorithm to show Clifford can be computed efficiently. The previous algorithm is more algebraic, but here there is a topological algorithm. And this question is explicitly asked by Jacob Belmonte in 2017.
So sorry, what is this theta here in the match gates?
Theta is a continuous parameter, a real parameter. Like e to the I theta x.
Okay.
It's continuous parameter.
This funny photon-like line. Feynman diagram.
Yeah, just a pair of Majorana fermions. So then for match gate, we can represent everything just as a ball with decoration on the boundary. And those are generating tensors of match gate. We can have all of them. And essentially, we can show when we have contractions, we can still keep everything on a ball. We can kill the holes using the stringiness relation. And that's a generalization of the Kirby color FT. And another thing is in Clifford, we can have those generated tensors, and you see there's no parameters when we have those bridges. And actually, we know this already like 7 or 8 years ago. So the major difficulty is how to compute them efficiently. And actually, at that time, I know how to compute the match gate efficiently, because essentially we have those like 4-valent diagrams on a sphere. It's just 2 boxes in planar algebras. And I'm quite familiar with how to compute that efficiently. And the algorithm, rather than the Pfaffing, the new algorithm topological one is exactly in my PhD thesis, this Yang-Baxter relation. We have a polynomial algorithm to run that. But for match gate, somehow we are puzzled at the point. Now we consider this as a new complexity, and we try to find a better algorithm to compute both. And then what's the major difficulty beyond Clifford and match gate? It's actually neither the number of holes or the number of crossings, but the combination of the two. If the two structures are not entangled together, it's easy to compute. And when they are entangled together, like one crossing moving around the hole, this is a long-range phenomenon. This is the hard part, like classical computer. And then to reduce this one as a linear sum, we can replace that as a linear sum of 2 terms. So this essentially saying the complexity is characterized by topological entanglement entropy rather than the usual entanglement entropy.
Can you explain what is a magic hole?
Magic hole is in this 3D TQFT, we have 3 manifold, and we look at surface, we have those holes, the genus. And if we have those kind of decorations moving surrounding the hole, then the hole will be magic. Something like that. And then we can show for any tensor network, first we translate that using our generating tensors to a TQFT picture. And then we compute that using our algorithm, the Yang-Baxter relation for the match gate and surgery theory for Clifford. So that's the missing part we just at the beginning. But after we understand TQFT better, we find the right way to use surgery theory. It's a little bit more than the usual surgery theory in TQFT. It only works for binary field, not even for qubit. There's something amazing for just qubit. There are some very specific arithmetic properties. And after we combine all those together, we are able to compute all those tensor network as an explicit formula. And K is the number of the magic holes. And so that's that part you see the exponential computational complexity. And for other part, this is just some combinatorial number, which we can compute efficiently. And that's the Pfaffing matrix, which can be done in polynomial time. This is a very clear algebraic formula. So essentially, we are doing the computation in TQFT so that the effort are given by the computation of surgery theory in the bulk. Match gate are given by those Ising type computation based on Yang-Baxter equations on the boundary. And then what's the advantage? The 2 computations are parallel. They do not affect each other. So you can take the advantage of both. This parallel computation for both a bulk and the boundary. So this dramatically simplifies the computation. And only when you see the magic hole, then both methods fails. That's the essential difficulty. And then we have this unified method so that we can look at any quantum algorithm. Just take any quantum algorithm, we can try this classical simulation to see whether we can do this by classical computer. And actually, usually when we do simulation, we are trying this noisy circuit because that's the thing that people do experimentally. And there is a very nice method using the passive integral. So we can have a truncated computation of the noisy circuit. So essentially, ideal circuit like Shor's algorithm, we know that has quantum advantage. But what we really have in our life is the second one, the noisy circuit. What we can do by classical computer using this QAnon classical simulation method is the third one. So then the question is, this experimental implementation is closer to the ideal one or the classical one. So this gives a much better benchmark to show either it has quantum advantage or not. So we use this to demonstrate some examples. Like last year, IBM proposed a quantum algorithm to solve some meaningful problem. It's actually very elegant. Since the circuit has noise, how do they minimize noise? It's hard to minimize the noise by the hardware. So they try to increase the noise, like twice the noise and triple times the noise. And then they look at those output. And then they take interpolation. And then take mitigation by classical computer and try to reduce noise in that way. Very elegant idea. And then they try to implement this using noisy circuit and changing the rate of noise. And then use mitigation and try to argue, okay, this algorithm will work better. It's kind of something with small noise. And that's a variation of quantum algorithm. And exactly at that time, we have the theory to show almost for all variation of quantum algorithm, we lose quantum advantage. So we are looking at the examples. And when we look at that, we saw they publish this paper. So, oh, here is the example we can try. And then we try that, and again, it takes 2 months to write the code. And finally, we are able to do that by classical computer with shorter running time and higher accuracy. And also, we have a better mitigation method by classical computer. So somehow, in any way, we beat the quantum advantage proposed by IBM. And we have some comparison of those data. And the previous one are something run by like the green circle are their experimental results, and the blue circle are the one with mitigation. And we can implement those just by those lines in classical computer. So very precise. And for the last one, they don't have the experimental data, but we can also run some classical simulation as a prediction. And this is kind of just the phenomenon. Once we see a quantum algorithm, now we can always try whether we have a classical simulation. Okay, now if I give you this quantum algorithm, what would you try? So a very natural question is, we have this very beautiful Shor's algorithm. Why not try that? And actually, after we beat the IBM algorithm, we still believe Shor's algorithm is on the peak. Somehow we expect to use classical simulation to run Shor's algorithm, and we expect to see the quantum advantage of Shor's algorithm. And then we can understand the mathematical structure of quantum algorithm, and then build some other better algorithm. That's the original expectation.
So by that you mean like turn Shor's algorithm using tensor networks and find the magic holes, count the number of them, and see.
Something like that, yeah. And actually here we use something like that. Just in Shor's algorithm, we can see where we see the magic hole. It's exactly, Shor's algorithm has 2 parts. One part is more relevant to classical algorithm, the other is quantum free transformation. The magic hole only lives in the middle. So now we just add noise in this one layer, middle line. And then somehow theoretically we can see magic hole has quantum advantage, but once we have noise, it loses quantum advantage. So we test that. And then we see, okay, if we have this noise, then finally Shor's algorithm lose exponential speed up. Or any constant rate noise, it lose exponential speed up. So we are very surprised about that. And actually behind that, we found a more general phenomenon. It's not just for Shor's algorithm, almost for most popular algorithms. Just once you have some mathematical structure to show this algorithm is meaningful, then for the same reason, we can show it's not robust to noise. So somehow we learn the lesson from this Shor's algorithm. It's very hard to expect exponential speed up and robustness to noise. So what we can expect? Even though this admits some classical simulation, but the polynomial degree by classical computer is relevant to the rate of noise. Like say if the degree is n to the 100, then still we cannot do this by classical computer. N to the 100 is a huge number, even though it's polynomial. So in that sense, we can expect to find some problem that even though that has polynomial classical simulation, but still hard to implement. And secondly, we can see if we reduce noise by quantum error corrections, then this will increase the degree in classical simulation quite a lot. That also shows the importance of quantum error corrections. That's exactly what people are trying to do. For Shor's algorithm, we want to do quantum error corrections. So this gives a lot of new mathematical insights to see what's the real quantum advantage. And after I understand that, somehow I get a feeling, oh, in what sense we would expect quantum advantage. And then we found a very interesting algorithm. We found something very positive. When we found this classical simulation, we made a joke. We said, okay, maybe we shall somehow sold the stocks. And then we found a new algorithm. Then we said, okay, maybe we shall buy some stocks. This gives a very good. And this algorithm tell us how to solve polynomial equations over binary field. And we tested some numerical simulation recently. It's very efficient. And one of the major motivation of this is actually constructing subvectors. When we construct subvector, eventually we reduce that to solving some polynomial equations over binary field. And then we found some method by classical computer, but still it will be hard. It gets larger. And then we thought maybe we can do this by quantum computer. And now, yes, we have a very good quantum algorithm to run this. And this quantum algorithm can solve NP complete problem. And that's really crazy. All the NP problems can be solved in this way. But there are some worst case we cannot solve in polynomial time. We have to solve that but somehow in exponential time. But that's kind of the case we have to expect. Otherwise, quantum computer is too powerful, too good to be true. But still, we run this for random equations and it solve most of them very efficiently. So we can see a very good hope. But another thing of this algorithm is once we see the measurement, then we will find the solution of the equation. And this is something we can test in polynomial time. So that's an NP problem. This is the major difference from the previous random circuit or boson sampling. There you have the distribution you want to show quantum advantage, but how? There's a big question mark. Here, it's easy. You find a solution, you can check that. If you have a solution of the equation, you get it. And we have many examples by classical computer. It's just hard to solve such equations. We can just test those examples. If we just take some of them and try to solve them by quantum computer, then we get it. We get this meaningful quantum advantage. And we have a rough estimate that this may take less than 1,000 qubit. That means we can do this. At the beginning, I thought we can do this in 3 to 5 years. And recently, I talked with many experimentalists. They said, oh, no, we can do this much, much earlier, even in 2 to 3 years. So I think we can really see quantum advantage in recent years and see the power of that. And there will be many, many applications like optimization problems and like cryptography problems. After I solve this algorithm, I have another big question: how to do cryptography? So this can solve many NP problems. I don't know which cryptography is safe. Thank you.